So these are the notes then on work and kinetic energy. So we've been through sort of the intro handout. Here's the notes that go along with that. So jot down whatever you think you need. When work is done on an object, it may give it kinetic energy. In fact, can you think of a way that you could do work and not have kinetic energy? Like, could you only give it potential?
Leverage.
It's still moving a little bit, isn't it?
Leverage is still.
Yeah, right? Anytime you push on something, if you push through something, remember, work only happens when it goes through a distance. So if it goes through a distance, it has to be moving. So I think the word is not may. I think the word is it gives it kinetic energy. I think it has to, right? It might give more potential, but I think it has to give it some kinetic. In general, work done is equal to FD. We know this already, right? This is the derivation, by the way. Right? Work done is equal to FD. And that work done is converted to energy, right? That's the energy that's transferred, however much amount of work, your 40 million joules of gasoline energy, is converted to some form of energy. And that's equal to the kinetic energy gained by the object. We could also show that as delta EK. Delta, of course, meaning change. Change in kinetic energy, going from zero kinetic energy to some. Delta EK. Or KE if you prefer, same thing, right? Same idea, delta KE. Okay, so I've sort of set up the basic structure to get our formula derived here. Okay, so I need a formula for EK. W equals FD, but remember, from way back, probably like about grade 7, I think, I've seen it in my kids' science notes, F equals MA. So I'm going to take this MA, and I'm going to replace the F right there, right? And what am I going to get? I'm going to get mad. That's what I'm going to get. Not crazy teacher mad, just mass times acceleration times, just mad. W equals mad. W equals mad. Now, do you remember from oh so long ago, VF squared equals VI squared plus 2AD? It's a long time ago. Do you have a funny feeling that we can somehow work this AD and this AD together?
Maybe.
Not sure how, but we got a feeling, right? We can do some sort of substitution here or something or other, right? Now, generally, things begin at rest, right?
So 0.
Things are at rest, which means the VI squared can sort of just, you know, disappear. So I can rearrange that to AD equals V squared over 2. Now, this V squared here is the original VF, right?
So
Well, we'll just say V, right? Our final velocity is the velocity at the time that we're talking about. So AD is equal to V squared over 2. Now, I can take this AD, I can take this V squared over 2 and do what?
replace it.
And guess what I get?
1.
MV squared over 2. Is that not the formula that the handout just showed us? I think it is. Substitute this for AD, and we get the work done is the kinetic energy gain is equal to FD, which is equal to mad, or EK equals MV squared over 2. It's one of the simpler formula derivations there are out there. Well, the derivation is pretty simple, right? Isn't it? Wasn't that hard? We're done. That's why kinetic energy is equal to mv squared over 2. If you prefer 1/2 mv squared.
Can you go on? No, when it goes into the water?
No. All right, so what do we get up here? We got W equals FD equals mv squared over 2. Right? If an object starts at rest, what is going on here? If an object starts at rest, the work done is the total kinetic energy of the object, right? If something's just sitting there, you do some work to it, all that work is transferred into kinetic energy. What if it's not at rest?
It has potential.
What if it was already moving and you gave it a shove?
Still giving it work.
Then the work done is not equal to the total kinetic energy, it's equal to the change in kinetic energy. Right? If an object is already moving, the work done is the change in kinetic energy. Right? I mean, I think this is probably a better description right here, because if the work done is equal to the change in kinetic energy, if it started at 0, well then it is just the kinetic energy, right? So yeah, work done is change in kinetic energy. So let's find our way to some sample problems here. It'll take me a second. I found them. Here's number 1. I'm thinking you guys could probably do this one like right now. I'm thinking, could you not? A 25 Newton force acts for a distance of 16 meters upon a 2 kilogram object, which was initially at rest, assuming no friction, find its final velocity. You will notice a lot of similarities between this unit and the kinematics unit. A lot of the stuff is the same, except we're going to be sort of looking at things from an energy standpoint. So what do we have here? We have a force. It's 25. We have a distance of 16. That's going to give us our work. We have a mass of 2. I want to know the final velocity. I want to know the final velocity. Okay, so remember that work is equal to change in kinetic energy. Work is FD is equal to mv squared over, not r, there I made that mistake, didn't I? mv squared over 2. So force times distance, 25 times 16, which is equal to 400. My mass is 2v squared over 2. Isn't that convenient that the mass and the denominator of the fraction cancel out? I wonder if I did that on purpose. Change in kinetic energy is equal to v squared. So in other words, v here is simply the square root of 400, which is 20 meters per second. So you can do kinetic energy formulas in your head. Meters per second. Easy enough. Yeah? Probably 2 marks, right? One for doing this side of it here, the 400. Some people might want to do it as a 2-step thing, find the work, right? Then find the kinetic energy. Do it 2 ways, 2 steps. That'd be fine.
No.
Okay. What about number 2 here? A force of 8 newtons acts for a distance of 5 meters upon a 4 kilogram body, which was already moving, initially already. Kind of redundant. Traveling at 4 meters per second. Find the EKI. What do you think I mean by EKI? Initial. Yeah, initial kinetic energy. The work done, EK, final EK, I guess would be EKF, and then find the final velocity. You think I can, what do you think? Are you guys good to go with this one, do you think, or should I do it? Do it? Okay. So EKI, initial kinetic energy. EKI is going to be mv squared over 2. The mass is 4. It was already moving at 4 meters per second. Square that. Divide by 2. 4 squared is 16. Times 4 is 64. Divided by 2 is
32.
32 joules of kinetic energy. 32 joules of kinetic energy. Now part B asks us to find the work done. Force times distance. We have 8 newtons of force. We have a distance of 5 meters. $40 joules of work. What happens to that 40 joules?
Minus 32.
Do we subtract it? It doesn't say that it's, you're right, actually it doesn't point that out, Drake. I think you have to assume that the force is in the same direction that it's already moving, right? It doesn't say it isn't, but if it was in the opposite direction, like let's just say the thing's moving to the right, it's got 32 joules of kinetic energy, and I sort of give it a push of 40 joules. How much should it have when it's done? 72, right? But what if it was the other way? What if I've got 32 joules of kinetic energy and I apply 40 joules in the opposite direction?
It's going to go 8 joules, 7.
And you're right. In fact, it's going to stop and even go backwards a step. Right? So it doesn't actually say. We'll assume, I think in this case, that it's going to be in the same direction. So my final EK, my EKF, well, maybe I should first of all say my delta EK, my change in kinetic energy is 40 joules. And now I can say change in kinetic energy, delta EK is EKF minus EKI. 40 solve for the EKF minus 32, which when it goes to the other side becomes a plus 32, which of course means my final kinetic energy is 40 plus 32. It's now got 72 joules of kinetic energy. That's not too bad, is it? And part D now asks for final velocity. EK is equal to mv squared over 2. 72 joules is the final kinetic energy. The mass is unchanged. 4v squared over 2. So my v is going to be 72, 4 divided by 2 is 2, so 72 divided by 2, and take the square root. 72 divided by 2 is 36. The square root of that, I think, is 6, is it not? 6 meters per second. Okay, so that's an example where the push is in the same direction as the object is already moving. I think number 3, I think there should be another side there. We got a 2 kilogram mass initially moving at 20 meters per second. It slides 150 meters on a rough surface where it experiences a force of friction of -2. I guess that's how I could tell that this one was in the same direction, because the force is positive, so is the speed. You can only assume it's in the same direction. Here, though, we've given the force of friction is -2. This is exactly the same question, except what? Force is in the opposite direction, right? How about you guys try number 3? Follow that template I showed you number 2. It's exactly the same, except the force is negative, which means it's going opposite and it's going to be slowing down. All right. So exactly the same steps. We found our EKI using mv squared over 2. 2 times 20 squared over 2 is 400 joules. It's got 400 joules to begin with. The work done is -300. The minus just simply refers to it's the opposite direction. In other words, I take away 300 joules of the object's 400 joules, right? This is just a bunch of algebraic mumbo jumbo to get me to the point where EKF is equal to 100, right? And once the final kinetic energy is 100, it's pretty simple to find the final speed. So it's dropped from 20 meters per second down to 10 meters per second. All right. Number 4, I believe, is very, very similar. The only difference is this one, we've got a 5 Newton force. What distance must the 5 Newton force have acted in order to change the velocity of the 4 kilogram mass from 10 to 15? So it's going at 10. And now it's going at 15. There's a force here of 5 newtons. The question is, how long is the distance? Why don't you give that one a try? It's basically the same kind of thing, except now it's up backwards. Different order, that's all, right? Different order. This is the EKI, this is the EKF, solve for D. All right, so what did I do? I found the initial kinetic energy, and I find the final kinetic energy, which is relatively easy to do. We know the speeds of both, which means if I went from 200 joules of energy to 450 joules, what is my delta EK? Yeah, 450 minus 200, or 250 joules. I changed my kinetic energy by 200 joules, which is equal to my work done. Right? That's how much work I had to do. So work equals FD, 250. The force is 5 newtons. Solve for D, 50 meters. There you have it. Alrighty, we are almost out of time. You have some problem sheets there. I see there's a QR code on it. I haven't been doing that for a while, so I don't know how that still exists or not. But you can try that. For sure, the solutions I know are on Edline. They are, of course, in the green binder. And I can't remember if I posted them to Schoology or not. So let me know if you have problem solutions. Enjoy.